be going over today's Atcoder contest, Atcoder Regular Contest 111, and we're joined by a special guest, Neal. Yeah, Neal, you want to say hi?
Oh, hey everyone. I
Great.
was gonna say,
Oh yeah.
you you just started the stream, right? So maybe
Yeah.
maybe people are still like coming in.
Oh
Um,
yeah.
so
I guess
yeah,
we'll wait
maybe we could
a
just like
we'll wait a minute and just chill.
yeah, sounds good.
Yeah. So you guys may know Neal from Code Forces or Atcoder, where his username is Neal.
There's also Top Coder.
Ah yes.
So chat, I'm curious, how many of you did the round, and if so, how you guys did?
Yeah, definitely wondering how many people actually did the round. Oh, I should set up some links while I'm at it. Your Twitch is just Neil Wu, right? For everyone in the chat to join.
Uh, yeah, mine is just Neil.
Or sorry, not to join, but to follow later. Okay, someone said didn't get time to read E or F. I actually also didn't read F. Um, I wonder how many people left when reading A. Yeah, A was kind of actually a pretty tricky problem this time, I thought. Like, I feel like it required a bit of like thinking compared to maybe some of the usual A's, which are more implementation. Though I also might just be mixing up ABCs and ARCs. Yeah.
Yeah, I mean, ARCs are definitely like the A's are definitely harder. This one, I feel like this one was maybe about average, but I'm not maybe oh, okay. Actually, sorry. Looking back at previous ARCs, yeah, the previous A's are a lot easier. Um, I think this one is you definitely have to like do some like number manipulation on this one. Um, but yeah, in previous ARCs, all of the A's are rated gray according to Kenku, and I don't feel like this one is gray.
Yeah, I also feel like Kenku, for those who don't know, Kenku is this great site where you can look at all the past Atcoder problems. But I always feel like the Kenku ratings for the easy problems are like much easier than like I actually felt the problem was for me. I don't know.
Yeah, to be fair, yeah,
Like
the ratings for the first problem might not be great because
they're
if
always like a
someone doesn't
hundred.
solve the first problem, maybe they just don't enter, right? So
Oh, that too. But yeah, I mean, even for like arcs and ABCs in general, I feel like, I might have found a problem. Like I felt like it was kind of tricky, and then I look at it and it's like difficulty 500. Because I think the difficulty is based on whether you solve it at all, I guess. So like problems that I found hard to solve are still solvable. I'm not really sure. Um, cool. Um, okay, it seems like there are probably enough people here to get started. So yeah, I guess let's get started with A. All right, so oh, there's uptime. That's cool. Okay, sorry. Let me just rearrange my windows a little bit. All right, someone said, "Did you start?" Yeah, okay, cool. So let's start with simple math 2. It's kind of weird. There's no simple math 1. Maybe they just didn't want us to feel like this was too simple in case we had trouble with it. But basically what we want to do, right, is we want to find some power of 10. And I think actually it's not that important what the numerator is. It's just some function of n. So let's actually just let x equal 10 to the n. And we want to find the remainder when x over m is, I guess, modded by m. And the way that I approach this is, first, I approach this in a couple steps. First, I wanted to find x over m. And to do that, I kind of thought about it like, this. So if we're finding the floor of dividing two numbers, we're basically getting rid of the remainder when we divide. So if you get rid of the remainder before you divide, now you have like plain like even integer division without any worries about remainders or anything like that. As an example, if you want to take the floor of 10 over 3, then that's actually equal to 9 over 3. And 9 here is 10 minus 10 mod 3, which would be 1. Okay, so that was kind of the first thing that I thought about when solving this. The next thing that I thought about was to find x over m. So the first step I kind of did is replace x with x prime, which is going to be x minus x mod m, or equivalently, I guess it would be floor of x over m times m. So now we have this x prime, and the answer for x prime is going to be the same as for x, but it'll be easier to compute because we don't have to do any floors anymore. So now we want to find x prime over m mod m. And this I kind of just intuited, but let's see if we can actually prove it. But what I did is I basically found this mod m squared, and then I divided by m later. And I think that is probably not too difficult to prove. So let's say this is equal to y, which is like our answer. So that would mean that x prime over m plus km equals y. And then if you multiply both sides by m, you get x prime plus km squared equals ym. So what we can do here is we can compute everything mod m squared. Right, we have this, so we want to compute it mod m squared. And then we find our y, our value of ym mod m squared, and then you divide the m back out at the end. So let's see what the code for that would look like.
Yeah, and so in general, if you want to do like x divided by a floored mod b, you should just compute x modulo a times b, and that'll give you what you want. Maybe the easiest way to think about why that works is because if you think about an x and you consider adding a times b to it, or in this case, if you consider adding m squared to it, it doesn't change the result, right?
Yeah, wait, sorry. Was that actually a way to do this like more directly?
Yeah, so the way I coded it is I just computed
Oh.
10 to the n mod m squared.
Okay, and then you did the floor division of the remainder of that?
With m, yeah.
Oh, that's pretty cool also. Okay. Yeah, so
It's
I guess
similar
to
what Vatsal91 said in the chat.
oh, I see. X equals am squared. Yes. Okay. Cool. Yeah, that's a good explanation. Yeah, so to kind of tie that back to this, the idea would be that we don't actually need to subtract out this x mod m thing at this early step. If we do it later, we're going to get something like this, I think. Wait, is that right? Yeah, and then this thing would end up getting zeroed when you divide by m. So the way that I implemented it was just by this like kind of by this two-step method. So first I found this remainder that I want to subtract out. So then I found x prime, which is x minus the remainder. And then, oh, I guess there's one extra kind of implementation step, which I kind of glossed over. But it's also important to be able to compute this actual value of x modulo whatever you want. So in this case, we want to find 10 to the n mod some modulus, and the way to do that is to use binary exponentiation. So this is a standard technique where you can find the nth power of something in log n time by repeated squaring, basically. Okay, cool. So let's move on to B. Someone asked, am I streaming the ABC tomorrow? Yes, I'm currently planning to stream the ABC tomorrow, or more precisely, I'll stream after the ABC. I do not want to live stream the contest. Oh, before we move on, Neil, did you have anything else to add about A?
No, not really. That's pretty much it.
Cool. So for C, or for B, we kind of have this problem where we have a bunch of cards that have two possible sides, and we want to basically flip some number of the cards so that the number of distinct numbers showing is maximized. So let's just quickly look at their example here. So you have a card with 1, 2, you have a card with 1, 3, you have a card with 4, 2, and you have a card with 2, 3. And if you flip those so that, I guess, this one has the 4 showing, this one has the 1 showing, this one has the 3 showing, and this one has the 2 showing, you can actually get 4 distinct sides showing. So that's why here, right, they kind of explained the answer here would be 4. And then they have some other examples, including like this more complicated looking one. So the way that I thought about this is I converted it into a graph. So if you kind of think about, right, you have all these pairs of items. So you can kind of think about them as edges in a graph, and then the colors would be the nodes. So if you have 1 is connected to 2, 1 is also connected to 3, 2 is connected to 4, and then 2 is also connected to 3. And what we want to do here is basically, if each edge is a card, then we want to direct each edge so that it points to the side that's facing up. So here, the first card is showing 1, then the second card is showing 3, the third card is showing 4, and the last card is showing 2. And now what we want to do is we want to, now that we've transformed our problem, our new transform problem, we basically want to direct all the edges in some arbitrary graph so that the number of nodes with at least one incoming edge is maximized. Let me quickly skim chat. Some people are saying this is easier once you implement it as a graph or change it to a graph. Yeah, I guess so. I actually still found this harder than A even after coming up with the graph thing, just because I think A was the kind of problem where it's very straightforward if you're familiar with kind of the basic number theory tricks behind it, and then really hard if you have to kind of rederive them. And then someone else said, I thought of iterating over each pair and outputting the one with minimum frequency in the current array. I think I thought of something similar, and then I quickly came up with a counterexample that it didn't work. Like, it sounds like what you're describing is like a greedy algorithm, where you kind of like pick the rarest thing so far, and I think that doesn't work, but I'm not sure. Okay, so what we want to do here is we want to direct all these edges so that we can have each node have at least one incoming edge. And the way that I thought about this is as follows. So first of all, this graph could have multiple distinct components, but we can treat each component separately. And let me actually draw the graph from sample input 3. The graph from sample input 3 looks something like this. And you can see here that it is actually possible to make everything have an in degree at least 1 by pointing this stuff outward and then making this into a big cycle. And then we actually have 1 card left over, and it doesn't even matter what we do with it. So the way that I approach this is I thought about, like, there's kind of 2 cases for a connected component. Either the connected component is a tree, and it has exactly n-1 edges, or it's not a tree, and it has more edges than that. And it turns out that if it's a tree, you can only show n-1 distinct things, and if it's not a tree, you can show everything. So let's quickly explain that via a picture. So you can kind of imagine taking any given graph and DFSing it to get like a tree inside of it, like a DFS tree. And if you do that, you can just point every single edge downward. And if you point every edge downward, you achieve n-1 score. And the reason for that is that every node except for the root has an edge pointing downwards to it. And n-1 is also optimal because you only have n-1 edges. So if you only have n-1 cards, you can only show at most n-1 distinct things. And now the last step is we want to show that if we add any edge, you can achieve all. Okay. So the way that I thought about this is, let's imagine you have like any other edge in this, and after you've drawn the DFS tree, the other edge will point from some node to some ancestor. So basically what I did is I thought about, okay, so you have this edge, so we'll point this edge up. And now, whatever edge points down into that node, you could also point it up instead. And then you could kind of follow that up the tree, kind of flipping all those edges on a single path. And then you would end up having every node covered at least once, including the root.
You can also just pick the like red pointed node as the root.
Sorry, which one is the red pointed node?
The like first red edge you drew, the one that it points to.
I see. Oh, I see. You're saying make that the root and then also have that one edge pointing up.
Yeah, so like
okay.
Pick the
yeah,
root
that makes sense.
Intentionally as some node in a cycle.
Right. Yeah, so then you don't even have to think about the flipping, the extra stuff.
You definitely have an extra edge to your root. Yeah.
Yeah. Cool. So the core idea here is we transformed it into a graph, and did you also think about this way, Neal?
Yeah, so I've seen a problem like this before, but when I first saw it, I thought it was pretty hard. But since I've seen this before, I just like knew what to do.
Ah, okay.
And yeah, basically, if you think about this as a graph, then you end up with components, and then yeah, you just play with some examples, and then you realize you can always do like the optimal amount.
I see. Cool. Yeah, and I'm not really sure how I thought of this graph thing. I think so. I recently saw some problem that was like, the editorial said we have a bunch of pairs, so it's very natural to think about them as edges of a graph. And I think I've seen that on a couple problems in the past, so I kind of just thought, I have a bunch of pairs of stuff, let me see if I can transform it into a graph. I've also linked the Jamboard in the stream chat, just if people want to be able to see a previous page of it.
Yeah, I think maybe one way to think about it to before you get to the graph is like you can do at least do some greedy idea where if some color only shows up once,
Hmm,
you can definitely assign that, right?
right.
And then that's kind of like leaf peeling, right? And then after you peel all the leaves, you end up with a bunch of things that are cycles, and then you can kind of, I guess you can kind of hand wave that you can get all of the remaining colors, and maybe you can guess the problem this way. And then if you want to prove it, you can just realize that it's like a bunch of cycles.
I see. Yeah. Actually, after I drew this graph, the first thing I thought of was you can start with the leaves because you definitely want to have something pointing to the leaves because it can't hurt you later, I guess. And then like you kind of reach the same idea, but it's definitely like at some point you kind of have to get to some version of this proof that it's either n minus one or n to avoid like a lot of implementation.
Well, after you
Um,
remove all the leaves, it's n, yeah. And
right.
if you go back to that example, then like the um, the first Jamboard slide, the leaf is 4, and like the third card, I guess it was the third card, you can definitely assign to be 4
Oh, this one. Yeah.
without any concern because
Right.
um, you can just get that card and it won't hurt any other card. Yeah.
Right. Or like it might hurt another card, but like you got +1 from this card already, so that's like
Well, no, it won't hurt another card because there's no other 4.
oh, I
Like
see.
it's
Okay.
better to give it the 4 than the 2 because
Yes.
if you give the 2, you hurt some of the other cards in some sense. But if you give it the 4, you didn't hurt anything and you got one +1. Yeah. So maybe this example is actually pretty good for like helping you solve the problem because you realize the 4 is like a
Right.
leaf that you can remove and then the rest is a cycle.
I see. Okay. You're saying that using up like claiming 4 doesn't hurt any other cards because none of the other cards wanted to use 4.
Mm-hmm.
Okay. That makes sense. I guess the way that I thought about it, which is definitely more convoluted, I think, is you're not hurting like you're not hurting the color 2 by not picking it. Well, you might be, but you're helping the color 4 at least. So it's kind of like you can't get a better solution with this card flipped, but you might get an equal solution. If, for example, 4 comma 2 is the only card, right? Okay. Anyways, cool. So that's B. I guess I'll quickly look at the code and then Neil, let me know if your code was substantially different.
I used Union Find.
Okay,
Did you
cool.
use that or DFS?
Yeah, it seems like we probably did something similar then. So what I did is I used a union find to find each distinct component. And then what I did for each component is I found the number of edges within each component by just looping through all the edges again and then incrementing some array. And once I found the number of edges in each component, I checked whether it was equal to the component size -1 or if it was equal to the component size or a larger number. And then I either added n-1 or n for each component to the answer.
I
Is that
see. Yeah,
basically what
mine
you
is
did?
like it's like mildly different. I track edges in the union find instead. So like when you do a unite, it also does edges plus plus. Um,
Hmm. Okay.
Unfortunately, I had a bug from this. I had a wrong submit from this because I forgot to do edges x plus equals edges y when you connect x and y.
Okay.
Somehow that like passed all the samples. And then the other thing is that um, I guess I have like fewer if statements than you. When I get a component in the union find, I just add min of number of nodes and number of edges. But that's the same.
Number of nodes. Okay, I see. Yes, that makes sense. I thought about doing something that was somewhat similar to what you did, but a little different, which was instead of counting the number of edges in each node of the union find, I thought about adding a flag to each node saying,
Oh, like
does it
is
have?
tree? Yeah,
Yeah, exactly.
that makes
And
sense
then
to
what
me.
you would do is when you merge two things, you would make it like it's only a tree if both of the components, both of the separate components were already trees. But then
Oh
I
yeah,
thought
yeah, yeah.
like, I think I thought like the kind of same thing that you ran into. I was kind of like, I feel like if I try to modify this union find pre-written code, I might make like some small mistake. Um,
Yeah, I guess what you did
just
is
because
like
it's tricky to
less
like
error
update,
prone. It's
right?
just so
Because like
obvious.
yeah, like you've already written the union find, so like if you go in and change it, like there's all these like kind of little edge cases of making sure you merge things correctly. Like
Yeah, yeah.
there's not that many edge
Oh,
cases,
oh, you
but
incremented both U and V. You only have to do one.
is that
But
true?
anyway, yeah. Well, they're definitely connected, right?
Oh, yeah, yeah, yeah. Okay, that's true. I think I was like kind of thinking like
It's
yeah, cause,
kind of like counting degree and divided by two. Yeah, yeah. I mean,
yeah,
none of
like
these details like really matter. It's just like either way works.
yeah, that's actually a funny little tidbit cuz I specifically thought about this and then I was like, "Oh, I do need to add to both." And I think I forgot that I already merged everything beforehand. So I think I was thinking like then it does kind of matter, but yeah, like by the time we reach this loop, uf.findU and uf.findV are just equal. So this is equivalent to doing plus equals 2 on the first one. And then if you're dividing everything by 2 right after that, then you could have just done plus equals 1. That's
Yeah,
basically what
but
you're saying,
anyway,
right?
yeah, in summary, you can do union find here, or you can do DFS or BFS, just anything that finds components and counts edges.
Right. Oh, I guess if you did DFS the way that you would do it would be something like have the DFS return like if you found a cycle and then um like have it
Hmm.
return like the ore of all its children basically and then that's what you do.
Yeah, something like that. Yeah.
Okay. Cool. All right, let's see what people are saying in the chat. Someone said built a graph with the cards as the vertices and then switched to the other one. Nice. Um yeah, in general I feel like and yeah, some people are saying DSU. This is easiest to implement with DSU. Yeah, I definitely agree. Like, it's not hard to write a DFS or a BFS to find components, but it just feels so much easier to use union find, especially if it's like a pre-written. Well, I think if it's not pre-written, then maybe it's easier to just write a DFS. But if you have union find pre-written, then I think it just makes it like a little bit cleaner. Like it's easy to loop through the components later and have like the canonical leader of each one, things like that. I think it's one of those things that doesn't matter that much, but it's like a little thing to make implementation a little cleaner. Someone says, where
Hmm.
can I join Discord server of Neal?
Of
Neal,
me.
do you want to add a link? Huh?
Okay, I'll just pull it up. Also, I thought it was funny that Voxel91 said they used DSU, I guess, 3 times.
Yeah, I think I also used DSU a couple times in this contest. I remember doing the contest and thinking, like, too many of these problems I'm transforming into graphs. Well, I guess D was already a graph.
Yeah, D was like obviously a graph, right?
Yeah. Let me add Neal's Discord as a command. Probably not a great command name, but hopefully people can remember it. All right. Let's move on to C.
Oh, John's here.
John is here in the chat. Oh, I see. Nice. C was not really a graph, I thought. Okay. Um, that's fair enough. I thought about C as a graph like a little bit when I was kind of visualizing. Well, I guess I'll explain the problem first before moving on. Okay. So for C, we basically have some permutation and we want to like undo that permutation. And there's also some kind of tricky edge cases where, well, not edge cases, it's kind of core to the problem, but there's some tricky, wait, sorry. Does one of those Discord links not work? All right, I guess Neal, you can edit your command to a more correct one using !edit command. Okay.
Do you know if those links expire? Is that what it is?
Well, your link does look kind of short, so I'm guessing it expires. When you're generating the link, you can do edit link, and then you have to change the number of uses and change the expiration time. By default, I think
Okay,
it's
let me
unlimited
fix
uses
it
and
then.
1 day. Okay.
Oh,
Cool.
I see. I'll fix that, yeah.
All right. So for C, yeah, basically you have some permutation where people have the wrong baggage, and you want to undo the permutation and give everybody their own baggage or the correct baggage. And then there's some limitations on like swaps that you're not allowed to do. Yeah. So the way that I thought about this is, I did think about this as a graph a little bit in the sense that if you look at a permutation, I guess I'll draw out the first one. Whoops. So if you have like the permutation 3, 4, 2, 1, and you wanted it to become 1, 2, 3, 4, you kind of have like, well, 1 actually wants to have the thing that's currently in 3. Wait, sorry, I think I might have said that wrong. Yeah, 1 wants the item that's currently in 4, and then, or if you draw the inverse permutation, I think it's something like 4, 3, 1, 2. So 1 wants the thing that's currently in 4, and then 3 wants the thing that's, or I guess we can go to 4. 4 wants the thing that's currently in 1. Is that even, now I'm actually a little confused. Okay. Maybe I shouldn't have thought about this as a graph if this is what I'm doing. And then 2 wants the thing that's currently in 3, and then 3 wants the thing that's currently in 1. So you basically have like some cycle, right? But this is basically the same way that people think about permutations and decomposing them into cycles. So it's not really necessary to think about it as a graph. But if you're not super familiar with permutations, there's this really common thing that you want to do with permutations called cycle decomposition. So when you have a permutation, like let's say you have the following permutation. I'll make 6 go to 6. If you have this permutation and you imagine this as a graph, you end up having a graph that can be decomposed into separate components, and the separate components are all going to be cycles. So this is called the cycle decomposition of a permutation, and usually people just think about it kind of directly, but if you want to, you can think about it using the graph formulation, which I think might be especially helpful if you've worked with graphs a lot but haven't worked with permutations a lot. But yeah, so the way that I approach this problem is I kind of guessed that the minimum number of operations would be when you break your inverse permutation into cycles, and then you fix each cycle just using like n-1 operations, where n is the number of elements in the cycle. And then I just kind of tried a way to do it. So I don't know, Neal, did you think about this a cleaner way, or maybe have like a proof that it's correct?
Yeah, so basically you have a bunch of these cycles, and then you can do swaps. In general, when you do a swap on a permutation, there are two cases. The first case is the swapped elements are in the same cycle. what happens is, and you can kind of experiment with this and draw this out. But what happens is the cycle breaks into two smaller cycles. If you also do two things that are like directly connected by an edge and you swap them, you get a cycle with one less vertex and then a single cycle pointing to itself. So that's kind of the most straightforward way to kind of clean up a cycle into a bunch of self-pointing cycles instead. The self-pointing cycle is just pi equals I.
Oh,
And
wait, do you mind drawing that? I think it would be a little easier to visualize.
oh, okay, let me see. I don't have my drawing tablet right now, but
Oh,
I
I see.
can I can give it a shot. So yeah, this is. Oh, I think I have to refresh the Jamboard here. Are you on 4 or 5?
I'm on 4, but I can move to 5 if you want like more space. All right,
Oh, I see what
I'll
happened.
move to 5 so you have a little more space.
Okay, so yeah, a fixed point is just pi equals I. It's just a vertex that points back to itself. And then, yeah, if in general, if you have a cycle, um,
Do you want me to draw the rest of the cycle? I'll just let you keep explaining and I'll try to draw things.
and
Oh, you got
well, just a 4 cycle, and
it.
you pick two adjacent ones. For example, you pick um, this one, and you try to swap them. Then what you'll end up doing is you'll end up like this. Because like if this is 1 and this is 2, then 2 now points to where 1 was pointing, which is 2, so it points to itself. And then 1 now points to where 2 was pointing, which we could say is 3 here. And so, yeah, basically, if you take two things from the same cycle that are adjacent and you swap them, you are kind of like making one step toward reducing the cycles down to fixed points. You can also actually swap two non-adjacent things in a cycle. What that does is it like cuts the cycle there into two smaller cycles. So you can, for example, take a cycle of size 5 and break it down to two cycles of size 2 and 3, or
So,
kind of
what would that
any.
look like? So, like, here I drawn a cycle of size 5. So, you saying, like, if we swap,
Yeah,
like,
so like let's
these
say
two
like the
nodes,
bottom one, yeah.
then what would
Then
the final thing look like?
so then basically this edge is gone, right? This edge is gone. You add this edge. Oh, sorry, wait. No, that's not right. You add this edge, and then you add this edge. Because this bottom guy now points to where this top guy was pointing to, and then the top guy now points to where the bottom guy was pointing to, which is here. And so I guess if you can see past the x's, then you end up with these two separate cycles of 2 and 3. Yeah. So this is kind of the general, the more general way to think about your options for like decomposing a cycle using swaps. Another thing that's related but not relevant for this particular problem is that if you have two separate cycles and you do a swap across them, it will join them into one cycle. It's just kind of the reverse of what we're talking about here.
Right. Like, if you do the same swap twice, it's the equivalent of, like, a swap is the inverse of itself, is kind of what you're saying.
Sure, yeah. And yeah, so in this problem, I think your intuition is right. We should try to get everything while like always making progress, which in this case means that for a cycle of size c, we only use c-1 swaps to get it all to fixed points.
And if there weren't the weight condition, then that would just be like really straightforward.
Right.
But because of the weight condition, we have to be a little more careful.
Yeah. So I saw that Mango Lussie said something in the chat, which is it's trivially the least you can do as unrestricted swaps require that many. Yeah, so if you have like cycles, it takes at least c minus 1, where c is the size of the cycle, swaps to fix it, right? But I guess the part that I was a little bit confused about, and I kind of just guessed and then submitted, was with the weight restriction, is it possible that there's a solution that takes more swaps, but then it's impossible to do c minus 1 swaps? Does that kind of make sense?
Yeah, that makes sense. Basically, what it turns out is that if you don't have an invalid starting state, where they actually describe the problem, if AI is less than or equal to BPI, then that's an invalid starting state because person I cannot do any operation. I guess we're assuming that I is not equal to PI, because if that's the case, then we don't have to worry about that. But assuming that they don't have the right baggage, if AI is less than or equal to BPI, then we're not allowed to do anything according to the problem. So that's an invalid starting state. And then you can actually just show that if you have a not invalid starting state, you can always do it with the min number.
Okay. How do you show that? I guess that's the part that I'm...
Yeah, so basically you have a cycle, and then if we think about the different swaps that we're allowed to do, the kind of the easiest swap to think about is the adjacent swap, because the adjacent swap basically fixes one person and then makes this new cycle that's one smaller.
Yeah.
So the thing is that the person who gets fixed, we don't really care if their new baggage is bigger than them.
Right, like because they're just done.
They're just done, yeah.
Okay.
And so if we can just make sure that the other person, the one who is not fixed, doesn't end up in the bad situation, then we're good. And it turns out that the way we can do that is we just start with the cycle, find the smallest baggage in the cycle, and yeah, we can just move that one all the way around the cycle. And that way, because it was valid to begin with, then nobody will have a problem having the smallest bag.
I see. The idea here is that anybody who already has their own bag, we don't care how heavy their bag is. And then anybody who doesn't have their own bag, at the beginning, they have a bag that is light enough for them, and then you'll always either give them their own bag or a lighter bag. Or the lightest bag.
Yeah,
right.
Exactly.
Okay. Cool.
Oh, by the way, I think John wants to join, but you have to give him the streamer role.
Oh, what? I see. I didn't realize that. All right. John, you can join the Discord now if you'd like to.
Oh, John says you don't have to handle cycles, just repeatedly give the heaviest bag to who it belongs to. Oh, I guess that makes sense because... Oh, I see, because then whoever had the heaviest bag before, they're not getting a bag any heavier, they're getting a lighter bag so they can handle it. And then whoever got this heaviest bag is just done. Oh, that's probably way easier to code, isn't it?
Yeah, sorry, you're saying give the heaviest bag... Hello. Like the heaviest bag that's not already at the correct destination?
Yeah, like just go... Yeah, just go like in decreasing order of bag weight, and then give that bag to the right person. Which could mean if it's already at the right person, you just do nothing.
Oh, I see. Okay, and then you never give a bag twice. So
yeah,
like...
I guess you never give a bag twice.
So you always just... If somebody is done... Like when you give somebody the heavy bag, they're done, because that's like the definition of our algorithm, and then the other person is getting a lighter bag than they used to have, so like they're also like happy, or they continue to be like actionable.
Yeah, exactly that.
There can be some smaller bag that gets like moved around a lot, but you never like... Yeah, I mean, because once you give the person their bag, then that bag is done.
My audio might be kind of janky. I'm not sure.
Okay. Yeah, can people in the chat hear all three of us? Okay, awesome. Cool. So I guess let's look at the code. I guess I'll show my code and then we can maybe show John, you implemented it the nicer way, right?
It's probably roughly the same thing.
Okay, I
At the
guess
end of the day, you're doing transpositions and a permutation, so you're
all right.
yeah,
I
maybe it's slightly
guess
nicer.
I guess we can look at both. Neil, did you basically do the same thing as me? Or should I also
Yeah,
show
I
your
did the
code?
smallest thing. Yeah, yeah.
Okay. So what I did here is yeah, so I guess I actually did this a little bit. I made a little bit fewer assumptions when writing my code because I wasn't really sure what assumptions were important and not. So maybe we should look at Neil's code right after this. But basically what I did is I just, I read the input and then I look at how heavy the bag that each person currently has is. So that's BPI as we described. And then I find the inverse permutation that we want, and then I break it into cycles. And then what I did is for each cycle, I find the lightest bag as my starting point, and then I keep giving the lightest bag to the next person to fix to rotate the cycle by one effectively. And then I also had this check, which was if we ever reach like an invalid operation, just print -1 and quit. So I think that the thing that Neil was explaining says that you'll never actually reach this case unless you reached it like at the very beginning, like while reading the input. So like this, keeping track of all these weights like this is not necessary. Is that right, Neil?
Yeah, the way I code it is also different.
Okay, cool.
I guess the difference is like yours is O of n and mine is O of n log n, but I just sort by b, and then I go in order of that sort,
You sort.
and then I just move things
Oh,
around.
right. Okay, because you don't only swap adjacent pairs.
No, I swap only adjacent.
Oh, okay. I guess
Yeah,
let's
maybe you can pull up my code and
let's
just,
open it. Yeah.
that'll make sense. So Maciek, Dragula. So in either solution, the case that's impossible is just the thing that they described. If AI is less than or equal to BPI for any I, then it's impossible. Oh, and also I is not equal to PI, because if it is equal to EPI, we don't have to worry about them. If that's the case, it's impossible. And if that's not the case, then it's always possible.
Yeah. So here Neil wrote this at the very beginning. He just found the check if somebody's holding someone else's bag that's too heavy, then it's impossible. And then after that, you don't check that anymore, right? Because you already know it's gonna work.
After that, I can't I can't output -1 anymore.
And then Neil has these nice asserts just to make sure it's like exactly right. Did you write a tester for this, by the way, or do you just have the asserts?
Oh, it's just because I screwed up and I got a wrong submit.
Okay, I wasn't sure if you ended up writing like a brute force, or not a brute force, but like a test generator.
No, I didn't quite do that. Oh, well, actually, I like kind of did that. I wrote yeah, okay, so I wrote, I didn't write a brute force, but
Right.
I guess I wrote some random tests, and then I just made sure the asserts didn't go off.
Right. Because that always, as long as the asserts don't go off, you kind of know that this is right then. Because it does the minimum number of operations without the weight restriction, and then the asserts say that none of the operations are illegal. Something like that, right?
Yeah.
Okay. So let's see. I see. Okay, so what you're doing here is you're fixing each element of the cycle by switching it with the thing that it points to, but you're doing those in like this order of B as opposed to doing them in like going around the cycle in order. Is that right?
Mm-hmm. Yeah, well, I mean, when you hit a B that is the smallest thing in the cycle, you just fix that whole cycle.
Right. Wait, you hit a B that's the smallest thing in a cycle. Oh, I see. Okay. Never mind. I actually did misread this. So what you do is you find that B and you use it as the starting point, and then you go along the cycle in order. And then you like go on to the next B as long as it's not in a cycle that you've already repaired.
Mm-hmm.
Okay. That makes sense. Cool. That's pretty nice. So I guess this is like... So this kind of translates to be similar to what I did here, where I found the starting point for each cycle, and then looped through this cycle, and then neal went through all the possible starting points, but skipped the ones that were part of a previous cycle. Is that an accurate explanation?
Yeah, so I don't have to like make a list of the cycle, which makes it easier to deal with, I think.
Oh, that's really... I didn't even notice that. Okay, yeah, that's super cool. So what I did is I basically wrote this, which goes through every starting point, and then if it's already been visited, you do nothing. Otherwise, you build the cycle that starts at it. And then I go through all the cycles and rotate them appropriately. But neal kind of combines the cycle finding step with the finding the starting points in order step. If I understand correctly.
Yeah. By the way, so LRNQ asked about the analysis of round 695. So I did that yesterday on Twitch. So you can find it on my Twitch channel.
Oh, was that yesterday's div 2? With the
Yeah.
the very tricky problem A.
Link here. Oh, the problem A. Yeah.
Yeah. I remember that
I remember
one.
which one you're talking about. Yeah.
Okay, and then I guess we can pull up... Oh, what? We can pull up John's code. And see if it's, Wait, am I reading the wrong problem? Why does this have, like, a mod num?
I'm just usually too lazy to delete stuff.
Very nice. Okay, so I guess what John does is first he has this same condition where you check to make sure it's not impossible first. Then who has bag is I guess the inverse permutation.
Yeah, just the inverse permutation.
And then you start
And you
with...
sort them from largest to smallest.
Okay. So you sort the... Okay, so you're sorting them in the reverse order. Okay, cool. So I guess this is actually very similar to neal's code, except, like, in terms of what the code vaguely looks like at the end. Except,
Yeah, except
you
I don't have
you
to follow
don't go through the
cycle.
whole cycle, you just do one swap and then move on.
Yeah.
Mango
I guess-
Lussie says, are all your codes n log n? Sorry, John, what were you saying?
I guess you and neal both probably generate the same operations, more or less, right? And this will generate like a slightly different order of operations.
Yeah, I think
So
that's
we'll
right.
start with
Yeah, I think neal's code and my code should give identical output. And I guess yours finds like another order that's still good.
Yeah.
Yeah. So Mango Lussie asked if all the codes are n log n, and I think mine is just O of n. Because I find the
yours is
minimum
n.
instead of sorting.
John's and mine
So-
are n log n, but actually I don't know if John's is super easy to make into n. I mean, mine is the same as yours, so it's easy.
Right. Cool. And then someone else said that theirs is n times the inverse Ackermann function of n. So I guess, wait, that's actually kind of a cute idea. So you found the cycles using a DSU, but then what did you do like within each cycle? Oh, I
assume
guess
just
I
the
guess
O of
within
n
each
stuff.
cycle you just find an arbitrary starting point, and then that gives you the cycle.
Yeah. You
Okay.
don't, you don't really need DSU for permutations though. You just follow the permutation until you repeat.
Right. Yeah, I think there was one contest that I did a while ago where like I used a DSU for like one of the problems, and then after that I was just seeing it in every problem. So I guess it sounds pretty similar to Vatsel's experience on this contest. Like I think I used a DSU. Okay, this is what I did. I wanted to like loop through an array and merge like adjacent blocks. So instead of just using like a for loop, first I like used a DSU to like merge everything with their neighbors if it was equal. And then I looped through the components of the DSU, which is like super unnecessary. But but yeah. Okay. So awesome. Let's move on to D. I think I have a reasonable explanation of this, and then let's definitely chat about E next, because I actually didn't solve E during the contest, and I'm excited to hear how Neal and John approached it, because I think they both solved it. Okay. So, D. By the way, John, you should also have access to the Jamboard if you want to write anything while explaining something.
Okay, yeah. I don't really have a tablet or anything, but maybe.
Yeah, I guess even drawing something messy with your mouse is probably a lot easier to follow than describing something out loud,
Yeah,
or even like typing with the text box tool or something.
I can defer explanations for E to Neil, who probably did the same thing I did. But yeah.
I see. Cool. Okay, so for D, we're given an undirected graph, and then they tell us how many vertices are reachable from each vertex, and then we have to direct the graph in order to... Basically, like the way that I thought about this is kind of like they already have a graph in mind, and we need to like find that graph or an equivalent graph. Because they give this nice constraint, which is they'll only give input that has a solution. I think it might have been substantially more difficult if that wasn't the case. Maybe it would end up being the same thing, but then you just... Actually, I think it would end up being the same, but then at the end you just have to like do some bookkeeping to check everything. So it's nice that they kind of saved us from that. But anyway, let's look at the very first example. They have this graph, and they say that from each node there are 3 things reachable. So the way that they do that is they just draw a cycle. That way everything is reachable, and everything is the same amount of reachable stuff. And then there's another very simple example here, where you have 1, 2, 3 as the amount of reachable stuff. So here, their solution is like this. So you can see from this node, only 1 thing is reachable. From this node, you have 2 things reachable, and from this node, 3 things are reachable. So the first thing that I thought of here, well, first I thought the input and output format was a little weird. Mostly the output format I thought was a little weird. So I was thinking like, wow, this seems like it's really annoying. We'll have to do a lot of bookkeeping. But then I kind of thought, well, what if we don't have to do a lot of bookkeeping? And that actually kind of guided me toward a solution, which I thought was kind of funny. But basically the idea is that if you have an edge, you kind of have 3 cases. You have like the first node has more reachable vertices than the second. The second node has more reachable vertices, and or they have the same number of reachable vertices. Cool. And Mango Lussie said that the complexity would be worse if you had to actually check. Oh, I see. So actually finding this kind of reachability thing is not possible to do faster than O of NM with like a nice constant factor from bit sets. Okay. So I guess that's why they didn't do that, which is good. Okay, so basically the idea here is like, if you have 2 vertices with an edge between them, let's say like this, then you kind of have 2 cases. Like, you definitely know that, let's say this is CU and this is CV. You definitely know that CU is going to be greater than or equal to CV. And the reason for that is that from U, you can just reach everything you can reach from V. Plus, you can also reach U. And possibly like other stuff as well. And the way that it could be equal is if U is actually reachable from V via like a cycle. So at first I thought I'm basically done. I'll just go through and for each edge, I'll just check which one has a larger count and then direct the edge based on that. And then I basically just have this edge case of when stuff is equal. And then it turned out that actually is a bit trickier. But I guess I'll open up the code just to show the first part of that. Just to make sure everything's kind of clear. And then I'll delete that. Cool. So what I did here is I just kind of looped through all the edges and then I either made them point left or right, or I kind of saved them for later. And so the pointing left and right part I think should be pretty clear, and then the saving them for later part I did find a little confusing. Is this basically how you guys approach the problem too, by the way? Like so far?
Yeah. If C's aren't equal, you have to do action, and then you just handle the equal C's, and like the equal C's become their own individual components because you don't have to worry about
Yeah.
like you can't go from some C down to some smaller C and then back up.
Right. Yeah, so I guess the key observation is that if you have a bunch of things with equal C's, wait, actually, sorry, what do you mean by they're their own component?
I think you want to break the graph into components by equal C. So
Yeah,
Right,
you can
okay.
ignore the different C edges at that point.
Ah, I see, yeah. So once you delete all the edges that point between things of different C, like, let's just say you had an example like this, where you already know this edge points like this, like, that's great, sure. This edge points like this, so then this answer will be like whatever it is plus all the stuff in here. But we don't actually have to think about it anymore. And I think that's basically what you guys are saying, right?
Yeah. One other thing I'll mention with this problem is that the way they phrased the guarantee was kind of annoying. It's like second thread's pet peeve.
Wait, was it really? I thought this
about
one
it.
was okay.
So it wasn't clear to me at the beginning if they're saying they'll only give you inputs that have a solution, or if you can prove that every input has a solution. And I was thinking about setting a clarification, but then I realized it's obviously not always possible.
Right, because
For
you could
example,
just
if-
make C like
could
n
just
for
make
all
n
of them and
0.
like have no edges.
Yeah. So it's like, okay, it's
Um,
clear which one they mean if you think about it for a minute, but
Yeah, I guess
anyway.
I had kind of the same thought, but then I thought that it was kind of clear because there always exists a valid solution is under constraints. So I thought like, well, it's a constraint, right? It's not like a note.
it's not like a mathematical note about the problem or something, I guess.
Yeah.
Yeah.
But yeah, it was still slightly like I guess they could have phrased it even more clearly and said like, we will only give you inputs
give
for
you
which there
inputs,
is
yeah.
a solution. But I kind of thought this was better than usual, at least on this dimension. Anyways, yeah. So once you break this graph into components that all have the same C, you might have like some component like this, and you basically want, because they all have the same C, you want to make sure that this component is strongly connected. So you want to direct all the edges so that it becomes strongly connected. And I actually thought about how to do this for a little while. And then what I ended up doing was like doing a DFS of the component and then directing each edge along like what I ended up traversing in the DFS.
Yeah, so you find the DFS tree, you point all the tree edges down, and then you point all the non-tree edges up.
Yeah. So I guess I'll draw a quick example of a tree just to make sure that's like clear to everyone. So if you have some tree like this, you can, and then you have some, I'll draw the up edges in red. And you have like some various up edges, you can point all the main edges down, and then you can point all the other edges up, and then that ends up making the graph strongly connected. Yeah, and I was actually slightly confused about why this was the case. Is there
Yeah,
like a really
well,
obvious way to
so
see this?
It only makes it strongly connected if the graph is bridgeless.
Yeah, it's about bridges. So if there's a bridge in the graph, then you're just out of luck. There's no way to do it.
A
If
bridge
there are
is
no
a
bridges,
single edge that connects two otherwise separate components. Is that right?
Yeah, if you remove
Yeah.
it, you get two separate components.
Okay.
yeah. And then if there isn't a bridge, then every edge has a back edge passing over it. So if you just point all of the back edges up, then you're good. Your example on the left actually has one problem on the like roots right child.
Yeah,
Oh, oops.
like that's not strongly connected.
Right. So I guess there could be an edge like that. Okay, so this would be an example of a graph with a bridge, and then if you have a bridge, then you have to point this in both directions, which you can't do.
Yeah, but luckily they won't give you anything like that because there's always a solution.
Yeah, technically your fix isn't valid because you can't have multiple edges.
Okay. Got it. Let me fix this some more. All right, how's that? Is this now a legal input?
Yeah.
It seems to be legitimate.
Okay. Anyway, so the way that I implemented this was, I think, kind of messy. So I'll show this first, and then I'll show. I mean, you have this. Let me delete that, and then I'll show either Neal's or John's code, assuming
So
that
I
they're
don't
a
have
bit
code for
cleaner.
this. I did not finish it in time.
Oh, I see. Yes. So John did E instead. Okay.
Many.
So yeah, I guess I'll quickly show this, and then I'll open Neal's code and see what we can learn from that as well. But basically, I did a DFS, and then if pointing all the down edges down and then pointing all the up edges up is kind of the same as just pointing all the edges in the like direction that you try to traverse them. So I basically just wrote this DFS and then directed each edge like this in the order that we try to go over them. And then I just had this little thing where you only set an edge direction once, and the reason for that would be that the way that I wrote my DFS, you would try to traverse back to your parent, so you'd end up like reversing. You would end up pointing all the edges up, I think, which you wouldn't want to do. Anyway, so I did that, and just as a like very small tidbit, like this is kind of my personal preference, but I wrote this stuff up here. So I have left and right, and then I have this separate thing that maps that into the output. And the reason I did that is just because I would hate to write all this code and then typo like the string for left or the string for right somewhere. So using constants, I think, always makes it easier to avoid those kinds of like little mistakes when implementing. Cool. All right. Neal, shall I display your code?
Sure. I just looked at my code and I realized it has a bunch of things that don't make sense in there, so I'm submitting another one.
Okay, great. Do you mean like you like were iterating on it during the contest and then you just kind of submitted something messy?
Well, it wasn't super messy. I just did something that's like, I started doing something, then I realized you don't need to do that, but I kept that loop in, and it doesn't matter. Anyway, I have two submissions now. You can, it's up to you which one you want to look at. If you want to look at my first one of the stupid loop, then
yeah, I guess we'll look at both to learn more about the process. And then Mango Lussie says that we should show theirs, so I'll do that next. All right, so this is the first one.
This operation of like taking an undirected graph and directing the edges to make a directed graph, a strongly connected directed graph, is like sort of a well-known thing. It like has a name. It's called strong orientation.
Oh, okay.
You can just look up code to do this if you want, but it's not much harder to look at DFS.
That's cool. I didn't know that name.
I see. Graphs with strong orientations are exactly bridgeless graphs. All right, that sounds familiar. Oh, cool. Yeah, and also if you finish the contest, you can learn about traffic control to kill time before my stream. Okay. So I guess I'll just look at Neal's second submission. So all right, so Neal has his answers array. And then set answer. Okay, cool. What is this?
It's the not equal case.
Okay. Sorry, I'm just a little confused about how I should best read this. Okay, is this basically like an if statement?
Well, it's just like the when you take the edges, I make one from A to B and one from B to A, but those have to be tracked which one is which because of the output format.
Oh, got it. Okay. I see. So you set the answer. Okay. Does this actually end up setting every edge twice then?
I guess this sets
Like,
every not
but
equal
it sets it to the same thing twice.
yeah.
Okay, cool. I see. Okay, so I guess Neal transformed his input a little bit to.
Well, except set answer only allows you to set it once.
Oh, I see. Okay. So only if it's unset will you set it, and then but even if you didn't have that, this would probably set it to the same thing twice because of how this works. Okay, great.
No, the set answer is only important for the DFS because you want to make sure you set it when you have a back edge. You want to set from the lower node to the upper node because when you finish the DFS, you'll go back to the upper node and look at the lower node again, and you don't want to set it at that point.
Okay, yeah, this is like the same problem that I. Oh, I see. Okay. Yeah, I think I was a little bit confused about this actually because I think my code was wrong, but then it worked for the samples. So I was thinking the problem would be that you go from a node back to its parent. But I think there might be even another issue on top of that you were describing. But anyway, yeah, if you just make sure you don't set things twice, then this actually works out. And then it looks like this is... Oh, I see. I guess I have broken this into more cases than I need to. Yeah, I see. So I have this separate case for if we've already seen things. Because at first I was thinking we'll want to reverse those edges. But it turns out that the way this is implemented, you don't care about that. So this is kind of duplicated. And then otherwise, I think Neal's code is pretty similar, just cleaner, without the duplication. Okay, cool. And then yeah, so you DFS starting from each node, and that's like a nice way to hit every component once without any issues.
Yeah, I guess I don't actually have to check the parent thing here because of set answer.
Ah, okay, cool. Okay, and then I guess let's quickly look at Mango Lussie's code. Is your username just Mango Lussie? I assume. Wait, hold on.
Take out the underscore.
Ah, I see. Does Atcoder not allow underscores?
No, it does. Scott's username is
Right, okay.
underscored.
Wait, what's
that's,
up?
That's pretty funny. See what
Oh. Oh, so you have both accounts on Codeforces. And then, can you not reset password on Codeforces? Or did you also use like a throwaway email or something? All right, I actually don't completely follow this solution. Neal, do you?
Oh, sorry, I wasn't looking at it. Let me see.
So I think the solution is just you start at something with maximum C,
Mm-hmm.
and then just run a DFS from that node, and then you're done.
Direct.
And then just orient things the way you did on end, like in the direction of the DFS. Because this takes care of both parts of the problem.
You start with something from maximum C, and then you DFS out. But where is that? Why can't I like see
I guess
that
you don't
part
have
of
to
the
start at
code?
maximum C, as long as you eventually hit every maximum C. Okay.
Oh, I see. Yeah, you only allow edges where you go to something less than or equal to.
Yeah.
Oh, I see. Okay. That's like, I guess, this if statement at the top in the DFS. Okay, so you only go... Oh, I see. Like, basically, like, the idea is that if you imagine the... So you basically traverse, like, the actual, like, secret answer graph. And the way that you do that is, like, an edge is only, like, legal to traverse if it goes from higher C to lower C. Is that basically the idea behind this? Cool. Oh yeah, someone said that Mango Lassi has double accounts. That's true. I'll be reporting you to Mike. Okay. Cool. Shall we go over D? Or sorry, shall we go over E?
Sure.
All right. So yeah, I'm definitely super excited to hear about this. I started to try to solve E, but did not make much progress. I had kind of a weird visualization of it, where I drew like these two lines, and I tried to look at when they cross the horizontal lines at multiples of D. But yeah. All right.
I think it's actually a pretty good visualization.
Oh,
of
really?
this, I mean,
Okay. In that case, I'll draw the graph, and then I will turn the explaining over. Just because I have a tablet, so you don't have to draw it. Basically, what I did is I made this like the I-axis, and this like the like A plus BI or A plus CI axis, and you kind of have these lines. And then the stuff in between the lines is like the integers that you care about. So if you draw a horizontal line, I'll use a different color. If you draw a horizontal line at every multiple of D, you're kind of looking for vertical areas here that don't cross any of the horizontal lines. And then you want to, however many coordinates, like that's basically how I thought about the problem, but I was not able to map that to like a good solution. Okay, so take it away.
Yeah, so I started with trying to phrase the multiple of D condition. There end up being a couple different ways you can phrase it. But the one that ends up being the most relevant is that if there is no multiple of D, then I wonder if I can type in here. Let me see.
You can type in the Jamboard using the text box tool. The only slight gotcha is when you... Right? No.
Yeah, okay. So basically, the condition for not
But you
having
can,
a
like,
multiple of D...
You can type like fake math, I guess.
Yeah, so this is the condition for not having a multiple of D. It's basically
another way to think about it is like if you look at those two numbers, a plus bi and a plus ci, they have to be between two multiples of d. So yeah, essentially you can think about it and you can get this. You can also think about it. Another thing I wrote that ended up not being super helpful was a plus ci mod d is greater than the difference between the two. But this floor and division ended up being more useful. The reason is that actually, so basically from this, there's one obvious algorithm you get, which is just to iterate I up and check this thing, right? That's too slow, of course. But if you have, if you put in an upper limit of d minus 1, so basically I has to be less than or equal to this.
So, I guess just so I understand, it seems like this floor condition is kind of like, if you look at this graph, it's like mapping each thing to like the red line that's beneath it. And then two things need to map to the same line to be like completely within like a valid like to not cross a line.
Yeah.
Okay.
Yeah, and then you
Cool.
also get this condition because if I is bigger than this amount, basically the difference between a plus bi and a plus ci is at least d minus 1, and so there's definitely a multiple.
Right.
And then I actually didn't do these lines. I think John did. But what I ended up figuring out, and this took me a while, but what I ended up figuring out is that if I is at most this amount, and then these two floors are not equal, then their difference is 1.
Wait, what? Oh, okay.
It can't be
I
2.
see.
Yeah.
So you're saying like the length, basically the length of your interval is like less than d. So there's no way you could cross like two multiples of d.
Yeah. So it's either
Yeah.
0 or 1. So that makes it a lot easier to count. If we can just like find the sum of both sides, the b side and the c side, then we can subtract.
Oh, that's super clever. Okay.
Yeah, so now the problem turns into, okay, how do you quickly compute the sum of floor of a plus ci divided by d?
So let me try to write this down just so I think it's like clear for everyone, including me. So basically we're saying if we let like this term be bi and this term be ci, or c sub I. Let me know if you have preferred variables, or if those are fine.
I guess little b and c are fine.
Okay, cool. So we're saying that ci is either equal to bi or bi plus 1. And then we want to find the number of times that ci and bi are different. So
Or
that
actually equal, but yeah.
I see.
Yeah, same thing.
So we want to find the sum of like if like ci is not equal to bi, and then that would be the sum of ci minus bi, which would be the sum of ci minus the sum of bi. That's the transformation that you're describing, right?
Mm-hmm.
Okay, cool.
So I think one nice way to think about this is that instead of counting the number of i's for which none of the integers between a plus bi and a plus ci is a multiple of d, you can instead start thinking about counting the number of multiples of d between a plus bi and a plus ci for some range of i's.
I see. So like this summation is like counting the multiples of d.
Yeah. And then really the important factor you're using is that at some point, at some threshold which you can calculate pretty explicitly, you know that this number is always going to be at least 1. And then you can just stop your sum there. And before that it's always 1 or 0, which corresponds exactly what you want.
Right.
And another useful thing I think to think about is, so like in your drawing you can imagine counting this number of multiples as basically counting the number of lattice points inside some rational polygon.
Right. And the lattice points here would be like the lattice points where I is like a multiple of 1 and then like the y-axis is a multiple of d.
Yeah, so you probably want to first transform your lines by dividing them both by d.
Oh, okay.
Right.
And then it's like actually just lattice points.
And then it's actually just lattice points. And you're just counting the number of lattice points in some region.
Wow. Okay, that's pretty cool.
Yeah. So it's like a rational region. So it's a bit, you can't just use Fick's theorem, but there's good ways to do it, which boil down exactly, like basically to.
Sorry, what do you mean by it's a rational region?
Okay, so there's a couple different problems you can think of for counting lattice points and polygons, right? So one is you have a lattice polygon, which means that all the vertices of the polygon have integer coordinates.
I see. So you're saying like, for example, the bottom left corner of this triangle is like at like 0, comma a over d, which is like
Yeah, so
not an
It's
integer.
not an integer, yeah. If it is
Okay.
integer coordinates, there's like Fick's theorem, and you can use Fick's theorem to count the number of points inside.
I see. But here we can't.
Here you can't, but you can still do it. It turns out it's sort of well known that you can do this, and then it boils down to basically computing sums of floors of like a plus ci over d, which makes sense because you can like decompose things into
Right, like
trapped
like
points like this.
this kind of ends up giving you the same transformation that Neal made with this summation.
Yeah.
Yeah, this is a super cool problem so far because like I had a bunch of these individual insights, so like the problem seems like kind of elementary in a way, but I wasn't able to put them together the way that you guys were. Like I thought about this floor thing for like the bucketing, and then I thought about like this like drawing, but then like coming up with this actual transformation is pretty tricky. Okay, so I guess what did we do next after that, or to actually find this summation?
So there's some algorithms that are kind of like the Euclidean algorithm, I think, and you can do this in log time. I actually don't know all the details, but I found some like book code that covers it, and so I just submitted that.
I see. That's very
So
nice.
here's a link to that explains how to compute these sums and phrasing it in terms so actually I got messed up by this during the contest because I spent a lot of time trying to copy their code and get it to work, but it wasn't working for some reason, and then I just implemented it from scratch. But it explains the logic behind.
Wow. And this
how to
this
do
example actually appears to be like exactly this example.
Yeah, that's basically exactly what you want.
So that's
Because it
pretty
makes sense,
cool.
'cause you've reduced it to this problem.
I see.
Okay,
Yeah,
but
I guess like there's
I'm
a reduction.
confused how so many people got this.
Well,
I think
how many
that this
people
is
got
just
it?
Kind of known, right?
Like
You can-
100 plus? Is it that well known?
So let's see. Let me do show
Well,
rated
I knew
only.
it, and there's at least 100 people better than me.
So 92 rated participants solved this problem. In contrast to like 300 solved D and like 540 solved B.
Oh, also,
it's
I just
in
looked
the
at the
Atcoder
tutorial.
library.
Are you
It's also
serious?
Yeah.
That's why.
All right, let's look at the Atcoder library. Why would that even be in the Atcoder library? Like, it seems like I've like never had to use this before in my entire life. Wait, where is it?
It's in math.hpp.
There's
Oh,
this guy.
math. Okay.
Where's the documentation for this? Oh, document en. It's math.md.
Yeah.
It's floorsome.
If you read the README and the main page of the GitHub, it has like a nice website with the documentation, like an HTML website. Okay, so that's very interesting. This floorsome thing. Oh, Mango Lussie said I had the same reaction, being like, why is this in the library? Yeah, I'm so confused. Like, the library is normally like very standard stuff. Like all the stuff in the library is stuff that like I've seen like many problems that use it, like Flow or Fenwick tree or DSU. And then I remember seeing this in the library like a month ago and thinking like, That's weird. And then like forgetting it completely. Neil and John, have you guys seen like this specific function in competitive programming before?
Yeah, one time.
I feel like I've probably seen it at least once or twice.
Okay, like does this seem like a Atcoder library worthy to you?
No,
I don't know
I've
what
seen it
Atcoder
one
library worthy
time.
means, but
I don't know, like is it the sort of thing that you would expect like someone to have in like their competitive programming book?
No, it seems pretty niche.
Okay. So I guess even at a higher level this is relatively rare is I guess what we've learned. Okay. Cool. So Neil, you said that you solved this floor sum problem by finding like some book code somewhere online. And I
Oh
guess
yeah,
you
just
could
an
have found
old
it.
code that I had.
Oh, I see. Like you actually did it once before, so you like looked at your old submission or something.
Kind of, yeah.
Nice. And then John, I guess you just read this article and then copy paste it?
so I tried to copy paste the code at the bottom of it, but I
Okay.
failed at getting that to work. So then I just implemented it.
What do you know what went wrong with this or
Not really. I mean, I implemented
Okay.
the same thing.
Okay, got it.
It was
It's
a bit
just
tricky because I
like
had to translate from like fractions to not fractions. I didn't have a fraction struct or whatever. but-
right.
Oh, John just put the same link. Okay, I didn't actually realize.
Oh, is that the previous problem that you guys did?
No, this is just some Atcoder.
No, just open the problem.
practice
You'll see.
Yeah. The problem is well, it's actually here in the documentation. It's like their example problem.
Yeah, it's the same.
But like this is from like the library practice contest, which is basically like sample problems, right?
Yeah, this more just like test cases for the library. It's not even like they had some Atcoder library contests which had
Right.
like actual problems. This is not that contest.
Oh yeah. This is the practice contest, so it's like
Yeah.
unrated and it's basically test cases. Okay, cool. Okay, so I guess yeah, I guess we reduce the problem to this either via this geometric transformation or this non-geometric transformation, and then we copy this book code or figure it out ourselves or something. Okay, pretty cool.
It is a nice algorithm. It's like not it's not hard, but yeah, it's cool to figure out. Like Neil said, it's basically some sort of GCD type thing.
All right, so let's see if Socket's library has this. Otherwise, I'll have to complain. Numeric. All right, none of these appear to be floor sum. Yeah. All right.
Wait,
So
doesn't this? So I had a problem in my code, kind of a problem, where it overflows.
okay.
Actually, I'm not sure. I was not sure if my code would overflow. I was scared about that, but then I just.
Oh, I see. You're saying
I
because
have
you
10 to the
compute
8 cubed.
both floor sums
Yeah.
separately.
Yeah,
Actually-
it just like works because you subtract it out.
My
Oh,
backup
like
was to do
they
everything-
overflow in like a well-defined way. So when you subtract it, it like subtracts in a well-defined way.
Yeah, but technically, overflow on signed numbers is not well defined.
Okay, like it doesn't actually do it mod whatever, like you might think it would.
Well,
like
it does.
sorry, it does, but it's not specified to. Like it's UB.
Yeah, on unsigned, it's well defined.
Oh, okay. So did you just end up doing this with unsigned,
No, I just did it with signed.
and then hoped?
Like, I think basically what I'm saying is I think my code and I think all of the Atcoder library code might be depending on this undefined behavior.
Okay, I guess let's read the Atcoder library then. Because I'm thinking, well, I guess the Atcoder library, let's see. Yeah, it gives you an LL.
Well, maybe not. Maybe theirs is actually fine.
Well, it can't really be, right? Because
I mean, the thing fits inside the constraints they give. So as long as your thing
Oh,
actually
I
works
see.
for that constraint.
And then if you do that, does the answer work though?
Yeah,
Like,
the answer
sorry.
will actually always be within.
Oh, you're just saying, Neil, you're just saying intermediate computations in finding one of the sums might overflow, but the sums themselves won't overflow?
For me, yeah. I'm
Oh,
not
okay.
sure
Yeah.
now if that's true for them or not.
So then the
I think the
Atcoder
same
library
thing's true
might...
for me.
Wait, how do I...
Although actually, now that I look at my code again, maybe none of these things actually can overflow. Like there's just some places where I have like 3 things I multiply, but I don't think they're actually. They can't all be big.
Let's find their floor sum function. Alright, I actually don't know how to tell if this will overflow. I mean, it looks like they're multiplying n minus 1 times n at the very beginning. So can that just overflow?
No, n is at most 10 to the 9.
Oh, right, okay, I see. And then they're multiplying by a divided by m, but I guess that's a is less than m, so that's fine.
Well, not necessarily, right? Because this isn't the case for a is at least m. But oh, actually, yeah, never mind. So this thing can definitely overflow.
Wait, it can?
If like
We can?
if your a is 10 to the 9 and if n is 10 to the 9, right? Then don't you have like a
Well,
10
but
to the 18 by 10 to the 9 triangle?
but they say that a is less than m.
Oh, okay. Okay, so then yeah, so
Like that's like
That's-
one of their constraints.
I see. All right, yeah, then you have to be careful when you're using it, I guess. Like I guess
All
what
right.
I did would overflow because I did not assume that a was smaller than m when I wrote
I
it.
see. So I actually don't really understand this algorithm, but could you also just do the algorithm modulo some big number if you know
Yeah,
the
that was
answer
my
will be?
backup plan. You only do like a normal integer operation, so you can do everything mod some prime.
Okay, got it. Well, you have this floor division of m, but you can do that before you mod it, right?
Yeah, I mean the only thing you need to mod is the answer.
The
variable.
answer?
Everything else you can keep in log longs.
Okay, got it. Okay, yeah. So you could also just find the answer mod like 1 billion or like 10 to the 18th or whatever you need to do.
Yeah, just mod 1,000,009,000 or something. It should be
And you only ever add to the answer, right? You never even
Yeah.
multiply stuff by the answer.
which is probably why it's fine. Like Neil pointed out.
Right. Okay, cool. All right, so that's E. Definitely a pretty. So, are you guys still surprised at how many people got it, or?
I was not surprised at how many people got it.
Okay, I would be surprised if that thing didn't exist, but now that I know it exists, I'm less surprised.
Oh, I see. Because Neil, your experience was like, you had to find some like weird sum, and then you like remembered doing it a long time ago, and like most people wouldn't have like that niche
Yeah, and
experience
I
of
found
like
some weird code. Yeah,
doing like this exact problem before like 8 years ago or whatever you did. No,
Yeah,
sorry,
I kinda
not the
feel like
exact
if
problem,
that-
but the same subtask. I mean,
I kind of feel like if that weren't in the library, then this would have like, I don't know, 20 or 30 solves.
yeah, I guess this
Maybe.
is Yosupo teaching us all a lesson to like read his library.
I think more
Um,
generally, it's a useful fact that you can compute the number of lattice points inside rational polygons. Because a lot of counting problems you can reduce to counting lattice points inside some sort of polygons.
Really? Like,
Yeah, I'd say so.
okay, like in competitive programming or like in like your day-to-day
Yeah, in
life.
competitive programming. I mean,
Okay.
depends who's setting the problems, right? But there have been problems that, like, a lot of counting-ish problems, even ones which don't obviously involve lattice points, can be reduced to.
I see. Okay. And the idea is like, so in this case the polygon that you're using is like a super simple polygon that's literally just 2 floor sums like subtracted. But you're saying but the idea here is that you can transform any polygon into like a linear number of floor sums by like sorting the points.
Yeah, basically.
Okay. Do you have like do you remember like an easy-ish problem off the top of your head that you can transform like this?
Mm,
from like a
Let
past
me think.
contest?
Um, I'll try to find something. I don't have anything off the top of my head, but
Okay. Cool. By the way, are you guys doing top coder?
I am probably not.
Yeah, I'm gonna do it. You guys should do it.
Nice. Yeah, there's top coder in like I guess 1 hour. Is that right? 1 hour, 5 minutes.
John, don't you want to qualify for the North America Regional?
Maybe. I'm pretty busy this weekend.
Oh, you're okay. I thought you were gonna say like I'm pretty busy in general, so I don't have time for the regional.
No, I'm pretty
Um,
busy for the next week or two. But yeah, after
Makes
that, maybe
sense.
I'll do some top coders. I just did
Uh,
Atcoder because I like Atcoder.
cool. Yeah. Should we wrap up the stream, or do people have anything else to add before we wrap up? Neil and John, do you have anything to add?
Not really.
Okay.
No,
I didn't
I
look
think
at
so.
F at all.
I guess
I don't have to do
let's.
Same, yeah.
Yeah, F says, "Do you like query problems?" It's a nice question. Cool.
It's
And I
good
guess
'cause it's not a query problem.
oh, someone
Like
asked in the chat. Oh, sorry. Wait, you said it's not a query problem?
Yeah, F is not a query problem. F is great because I hate query problems, but
Wait,
it's not
what?
a query problem.
Oh,
Yeah, you should
No,
read
it-
F. The statement of F is like very
funny.
It's like a math combinatorics problem, as far as I can tell.
Okay, so there's a query problem, and then there's another query problem, but the
No, read the second query problem.
oh, I see. That's not a query problem. It's counting the number of valid inputs to the first query problem.
Yeah, or like the sum of all the answers to the first query problem.
Okay, I see. So this is just a counting problem, or not counting
Yeah,
exactly, but like a combinatorics
combinatorics
kind of
problem,
Mango Lussie said, "I wish F were a query problem." Nice. Um, all right, cool. Yeah, and definitely everybody in the chat. So Neil, are you gonna stream later today?
Oh, what do you mean?
I don't know. Someone asked if you're streaming later today. So
Oh, I
Are
wasn't
you?
planning to.
okay. So Neil is not planning to, but you should definitely follow his Twitch because he will stream in the future. Um, and yeah, definitely join our Discords. And this video will be on my YouTube later, so subscribe there if you want to go back and check it out. I typically upload within like 1 to 2 days of the broadcast. Yeah, I guess before we close, Neil and John, is there anything you'd like to plug other than the above?
Nope.
Oh, I'm curious if there's anyone in the chat planning to do top coder in an hour.
Oh yeah. Neil, are you considering doing a post top coder stream, or do you think that top coder is less stream friendly or less mainstream than Code Forces?
Yeah, I haven't done one yet. Maybe I could do like just like a chill stream going over some top coder around at some point. But yeah, I haven't done any post top coders yet.
I guess one thing about post top coders that I was thinking about is like top coder has so few problems, and then there's almost no overlap between div 1 and div 2. So it kind of limits like it's kind of like on if you're going over like a Code Forces div 1, like a bunch of the problems are in common with the div 2. So like div 2 viewers would still have done those problems as well. And also like I don't know, like because of top coder's format, like sometimes people don't even read all the problems because like the clock starts ticking when you start reading. So it definitely seems a
Yeah.
little bit less stream friendly than like a Code Forces round that has more overlap, or like a Code Forces round that has 100% overlap, like a global round or a div 2 only or something.
Yeah, I mean, it still has 1 out of 3 overlap, and then
Right.
you could just live solve the div 2 problems.
Yeah.
But yeah, they're definitely less attended than, say, code forces
Yeah, for sure.
nowadays.
Um,
It is interesting because it was Topcoder was like when I was getting into competitive programming, Topcoder was the big place to compete, and code forces didn't exist, and Atcoder didn't exist,
right.
and all these other places didn't exist. So Topcoder was like the OG competitive programming place.
Yeah, that's definitely true. And now I guess mostly like I think it's people who used to do top coder, or people who do a ton of contests, right? So if you want to do like as many contests as possible, then you're gonna want to use every contest site available. But I think yeah, as you were saying, I think now most people kind of start on like either Code Forces or Atcoder.
Yeah, it's admittedly more setup because you need like the arena and
yeah.
you probably want to plug in and so on. Yeah.
Yeah, and like if you're using C++, you have to make sure your stuff works with C++11, things like that. Cool. So one person in the chat actually said they are doing top coder, and then Mango Lussie asked if we're planning to cover F, and the answer is, I guess no, because I think none of us really thought about it that much yet, or, I mean, I didn't read it during the contest. But yeah, cool. I guess we'll end the stream there. Thanks so much everyone for joining, and I'm gonna be doing another stream tomorrow after the Atcoder beginner contest. So definitely encourage you to do the contest if you can, since I think streams are always most valuable if you've already tried the problems yourself. Cool. All right. Bye everyone.
All right. See y'all
And
later.
Thanks for joining, Neal.
Sure thing.